Canis' original survey revealed several problems: a rusted keel, blisters on the hull, keel bolts badly needing replacement, and a weeping rudder. From this list, I gave the yard, the hull, and the keel jobs, and left for myself the rudder and the keel bolts. At the time, I thought all that was needed was to drill a couple of holes, drain the water, and patch the holes. Needless to say, it took a bit more than that. Once the anti-fouling was removed, something odd came to light. While the port side of the rudder showed no damage, the starboard side presented extensive cracks. This suggested some fundamental design problem. Let's start this story by first looking at why the rudder failed. For this, we'll first look at the forces acting on the rudder. As the water flows past the rudder, the flow lines need to distort to accommodate the presence of this hydrofoil. When this happens, the local pressure of the fluid changes. These changes in pressure are responsible for the forces that eventually will turn the boat. Let's look at them in more detail. To simplify the analysis, let's just look at the cross-section of the rudder. To look at what happens as the rudder turns, it's easier for us to turn with the rudder, making the water look as if it were changing directions. The large green arrow shows the direction of the flow. The graph shows the distribution of pressures along the surface of the foil as the flow changes direction. The curves turn blue to indicate negative pressures and red to indicate positive ones. This is perhaps easier to understand if we plot the pressure as arrows on the surface of the foil. The length of the arrows will be proportional to the pressure, and the direction and color will indicate whether it is positive or negative. We'll use red for positive and blue for negative. At 0 degrees, the pressures are equal on both sides, cancelling any resulting force. The boat then tends to remain on course. As the angle of the flow changes from 0 to 10 degrees, the pressure distribution changes dramatically. The first thing to notice is that pressures are very unevenly distributed over the span of the foil. This is particularly relevant for the design of balanced rudder like this one. For this design, the goal is that the turning forces or torque about the shaft almost cancel out, making steering effortless. For stability and safety, the designer usually leaves a small amount of resultant torque opposing the turn to automatically restore the neutral position. As the forces are so unevenly distributed, the shaft must be placed close to the fore end of the rudder to achieve balance. To understand why the skin cracked, let's first look at how the rudder was originally put together. The rudder was constructed by first laminating the two separate halves of the outer skin. First, the port side was laid down, the shaft with the webbing added, and then glassed in place. Next, the starboard side was added and the seams sealed. The factory then poured liquid polyurethane foam through 3 holes opened on the starboard side. Once the foam expanded and cured, those holes were sealed and the exterior finished. The fundamental problem with this design is that lateral forces are transferred to the shaft only through the foam. This works well under compression, but it's a poor choice under tension. Unfortunately, when turning to the right, the starboard side of the skin is put under compression, and due to the curvature of the foil, this results in the production of transversal forces pulling the skin away from the foam core. Now, remember those holes open to pour the polyurethane? Those should have been glassed over. Instead, they were covered with putty. The putty bonded very firmly to the foam, but rather poorly to the thin edge of the skin. With such configuration, it was easy for the skin to become detached from the putty, creating a path for water to enter between the skin and the foam. Keep in mind that Canis lives in the Chesapeake, where it freezes in winter. So as soon as water trapped under the skin froze, it expanded, creating a wedge which further detached the skin from the foam. The following year, more water got trapped and even more damage was caused during winter. Eventually, the whole skin became detached and water started penetrating the foam core, cracking it as it froze. We can see in the picture the detached putty plug outlined by the water seeping out of the rudder after haul-out. So now that I know why the skin failed, I needed to design a way to prevent this from happening again. The strategy I opted for had 4 main parts. First, increase the rigidity of the skin. Second, use heavier foam. Third, mechanically anchor the starboard side of the skin to the port side and to the webbing. And fourth, allow for no large holes through the skin. We'll see in the next episodes how I implemented these ideas.
Speak your truth, we already know. Set your mind, it's written in gold. Don't say no, let it unfold out, and we'll take the embrace. So still it's where I'm found. All I know is emotion notes, and the look on your face was here.